Okay. Hello, everybody. Good morning. Hope you're all doing good and welcome back to class. So, how many of you are there? Only 6 of you are there. Is there any problem? Like, is there any exam going on tomorrow? Why is the strength less today? Yes, tomorrow any exams are going on? Tomorrow anybody has exams?
No, sir.
Okay. Fine, but I don't know why the strength is so less today. Okay, fine. So maybe we'll start. Right. Start share the screen. Okay, right. So last class we were talking about molecular orbital theory, right? Right. So I told a molecular orbital is formed by combining two atomic orbitals, only two atomic orbitals. Right. And where are the atomic orbitals coming from? One each orbital comes from each bonding atom, one bonding atom. One bonding atom. Okay. Right. So if there are two hydrogen atoms, two s orbitals will combine to form two molecular orbitals, right? So two atomic orbitals combine to form two MOs. One of them will be constructive, and one of them will be due to constructive interference. The other one will be due to destructive interference, right? So whenever I have constructive interference happening, that one is what is called as molecular or say bonding molecular orbital, and whenever destructive interference happens, we call them as anti-bonding molecular orbitals. Okay, bonding molecular orbitals and anti-bonding molecular orbitals, right? So I told you these are more stable, right? These are less stable, right? So they oppose bond formation, right? Oppose bond formation, right? They favor bond formation, right? Because they're more stable, right? And I told you that basically molecular, in this case, we are going to take into the wave nature of the atomic orbitals, right? Each atomic orbital has one psi value, right? Now these psi1 and psi2 will constructively interfere or say destructively interfere, that is minus, right? To form bonding and anti-bonding molecular orbitals respectively. Very, very simple. This is the overall story, what we saw last class. Okay, right. Now, what are the different types of molecular orbitals I can have? Right. Now, for that purpose, let us look into this. I already mentioned this, right? Say now when I have S and S orbital, say you have to put plus and plus. Right. Now, what will happen? I am going to form a big molecular orbital, right? And if it is 1s and 1s, or say 2s and 2s, accordingly the name will change, right? So this is how the molecular orbital will look. So this I will call it as sigma 1s, right? This is a bonding molecular orbital coming from s orbital, two s orbitals. Okay, now this is constructive interference, that is plus and plus are interacting. When I have plus and minus interacting, see I put a plus sign here, but I put plus and minus. Right now, in that case, you will see something like this, plus, minus, something like that. You will have a node here. Node means that you cannot find electron density here. Right now, this is what is called as sigma star 1s. Star always represents anti-bonding molecular orbital. Okay, star always represents anti-bonding molecular orbitals. Right. Okay, now that is about s orbitals. Now remember, this sigma, right? This sigma again tells you how the overlap is happening, or say how they are interfering, whether it is a head-on interference or head-on overlap, or it's a lateral overlap. How do we have normal sigma on pi bonds? Same definition holds good here also, right? So obviously, if I have only s orbitals present, there is no other way than to form a sigma bond. Okay, than to form a sigma bond. That is very easily understood, right? We saw px, p orbital also, right? Now guys, remember I have px, py, and pz. I have 3 p orbitals, right? Now you have to first specify the internuclear axis. Okay, first you have to specify the internuclear axis. What do you mean by internuclear axis? Say I have 2 hydrogen atoms like this, right? Now there are two nuclei here. Now there'll be a line connecting this nuclei, right? This is what is called as what is it? Axis of what is it? Internuclear axis. Sorry, internuclear axis. Okay, this line connecting the 2 hydrogens is what is my internuclear axis. Now it is up to you to choose which can be the internuclear axis. It can be X or Y or Z. There is no restriction like that, right? But by convention, right, what everybody uses is Z, right? We say that this is Z axis. Okay, we say that is Z axis. Z axis is the internuclear axis. Right, that means internuclear axis means the line connecting the 2 nuclei. That is what is my internuclear axis, and we are going to take it as Z axis, but there is no restriction. Right, there is no restriction. Now, why do we say it like this? Is because, say for example, if I take PZ orbital, say PZ and another PZ, right? Now, if this was the internuclear axis, I would have had a head-on collision like this. If this was a Z axis and this was PZ, right? The PZ, I know how it is oriented. It is oriented along the Z axis, right? So PZ and PZ will form sigma PZ to PZ, whatever it is, right? But PY and PX, right? Now in the same thing I can show, this is PZ, whatever I draw. So if I take another color, now this would have been, say, my PX, and say another color if I use, right? Now say I would have had, this is my PY, right? They cannot form sigma bond, right? So because the internuclear axis is fixed, to PZ axis, obviously only PZ can form sigma bond, but the other two, PX and PY, will form only pi bond. But again, if you fix x-axis as the internuclear axis, then only px will form the sigma bond, py and pz will form the pi bond. Again, if you choose y, then py will form the sigma bond, the other two will form the pi bond. Very simple. But we don't have to have any confusion. We are going to fix the internuclear axis as z-axis, so that pz orbital will form sigma bond, py and px and py will form pi bonds. Okay, I hope it is very clear to you. Right. So moving on to see what happens if I have, say, first we'll take PZ, because we said that it is going to form sigma bond. We'll see how the sigma bond is formed. Right. Say PZ, I need to have head-on collision because it is sigma bond. Right. Say now 1, 2. Right. Say now what you have to understand is plus and plus should interact. That's what is more important. Right. Or if I put minus here, I should put a minus here. That means constructive interference, right? Now this happens, I'll form minus. So this is my sigma 2pz. If this is pz and another, okay, this is 2pz, I'm going to form sigma 2pz. This is constructive interference, right? Same way, I can have destructive interference, right? Plus and minus will interact. Right now, in that case, what will happen? I will form plus minus. This is again, you see there's a node. Always, whenever you have this is obviously going to be called as sigma star 2pz, because again it's going to be an anti-bonding orbital. Right? All the sigma anti-bonding orbital, I can tell you, all sigma anti-bonding molecular orbitals will have a node perpendicular to the internuclear axis. Right? You can understand from this previous case also. See, this was the internuclear axis. I can draw it. This was the internuclear axis. Now there is a node which is perpendicular to the internuclear axis. Same way here. This is the internuclear axis. right? But this one is going to be the node which is perpendicular to the internuclear axis. See, this is not important to you, but I'm just giving you a flavor. Nobody's going to ask you draw the molecular orbital shape and all. Nothing they're going to ask you, but I'm just giving you some insights. Okay, right. Now that's about PZ, right? Now let me take a PX or PY, doesn't matter. They're going to form the same thing, pi orbital. So how it is going to form, let me see. Right. Now in this case, it is going to be lateral overlap, right? Say one p orbital, another p orbital, plus, minus will interact. Again, I have to put a plus sign here because it is not plus sign because in the constructive interference, plus and plus are interacting, minus and minus are interacting. Okay, right. Now you see what is going to happen. I am going to have a shape something like this, a big positive, because two positives coming together to form a big positive and a big negative. Right now, what you see here, this is going to be called as pi 2px or pi 2py, depending on which orbit you're talking about. Right? Say this can be py 2px, 2py, 2py, anything. Okay, if any of them combine to form, they will combine to form pi 2py or pi 2px. Right now, strangely, this is a bonding molecular orbital. This is BMO, bonding molecular orbital, but still you see there is a nodal plane, but this is a different kind of nodal plane, is it not? Because in this case, the nodal plane or the node, or we call the node, is along the internuclear axis. Is it not? This is the internuclear axis, right? This would have been the internuclear axis, because this is where the sigma bond would have been formed, this way, this line which I'm talking. Right now, along this internuclear axis, right, you will see that there's going to be a nodal plane. Right now, this happens. So what you have to understand is pi BMOs, right, will have a node which is going to be along the internuclear axis. Okay, it is going to be along the internuclear axis, right? But sigma doesn't have it. One second. If sigma bonding molecular orbital is there, there is no node. If there is an anti-bonding sigma, that is going to have a nodal plane perpendicular to the new internuclear axis. If it is going to be pi bonding molecular orbital, it is going to have a node along the internuclear axis. Yes, what was the question?
Sir, for both PX and PY, the nodal plane will be along the internuclear axis.
Yeah, correct. So yeah, now you see that this is one idea. Now say, look at it like this. There is, hope you're looking at my video. There is one p orbital like this. Okay, this is, or how do I put it? Okay, say this would now you are seeing that this is along the plane, like this is like this, whatever you are seeing, right? Along the this whatever I've drawn here. Now same thing I can have like this also, right? Like this I can have, right? That also again you see there's an internuclear axis here that is going to have a nodal plane. So px and py will accordingly. So I just along the axis, what you're talking about, that's it. Okay, understood? They'll have the same shape. Pi 2py or pi 2px will have the same shape, but only the orientation will be different, right? So in this case, for example, if this was px, this would have been x-axis, right? If this was py, it would have been y-axis. That's it. That's the only difference. Okay.
Sir,
yes. Yeah.
Sir, for anti-bonding molecular orbital, will the lateral collision happen between plus and minus?
Coming to that. Right. So now that's about constructive interference. We found bonding molecular orbital. Now, when I go to anti-bonding case, let me see what happens. Right. So anti-bonding case, plus, minus, reacting with minus and plus. Right. So plus will interact with minus will interact with plus. Right. Now you see this is going to be destructive interference. So you will see that something is going to happen like this: plus, minus, plus. Right now, this is a pi orbital. I would say okay, this is a pi molecular orbital. Now you already see along the internuclear axis there is one node. This is the line, right? And since it is an anti-bonding orbital, all anti-bonding orbitals will have one nodal plane perpendicular to the internuclear axis, right? So this is what is called as pi star 2px or pi star 2py. Okay, pi star 2px or pi star 2py. Now pi star alone will have two nodal planes. Okay, one along the intermolecular axis because it's a pi bond. Second, since there is an anti-bonding orbital, it is going to have another nodal plane which is perpendicular to the intermolecular axis. Okay, this is how the shape will look. Right? I hope it's everything is clear to you. Right? S orbital, constructive interference, destructive interference, bonding molecular, I mean bonding, anti-bonding. And then if it is going to be PZ, it is going to be sigma star 2PZ, sigma star 2P, sigma 2PZ and sigma star 2PZ. And if it is going to be PX or PY, it is going to be pi 2PY or pi 2PX or pi 2PX, pi star 2PX or pi star 2PY. These are the shapes. And if at all you're interested, you can remember the shape. It will be useful for your JEE mains and NEET exams. But for CBSE, like for your school exam, you don't have to worry about it. Nobody's going to ask you the shapes. Okay, right, fine. So now we understood what are the different kinds. Even d orbitals can involve, but we are not going to look into it because it's very complex.
Sir,
right? Yeah, tell me.
Sir, what does the plus and minus signify?
I told you, no. See, if there is a line, if there is a wave, say this is the origin, this is the axis, right? Say now, if I have this thing like this, now this part which I have here, this is above the origin, so this will be positive. This is below the origin, this is negative. That's all that means. Right? Whether the wave is above the origin or below the origin, whether it's a crust or tuff, that's what is the matter. Yes.
Okay, sir, understood.
Understood? Yes, good. Right. Okay. So that's about the shapes of orbitals. Now we know what are all the different types of orbitals I can have. Right? Now I told you that you have to follow Aufbau's principle. Right? You have to follow Aufbau's principle for you to fill the electrons. Obviously, you're going to fill the electrons here. Right? Now, Aufbau's principle, I know what it says. The lower energy orbitals has to be filled first. Then we have to go for higher energy orbital for filling. Right? Now, I'm going to give you the order of the molecular orbitals. Okay? Now, the least energy is sigma 1s. Right? Then it should be sigma star 1s. Then it should be sigma 2s. Sigma star 2s, right? And then comes I think pi 2px equal to pi 2py. Both of them will have same energy. We'll have to put a negative equal to sign here. Okay. Then comes sigma 2pz, and then it is going to be pi star 2px equal to pi star 2py, and at last sigma star 2pz. Now remember, this will happen if the total number of electron is lesser than 15. Okay, or lesser than or equal to 14. We'll have it like this. Okay, if the total number of electron is lesser than or equal to 14. For example, say H2 will have only 2 electrons. Say C2 will have 12 electrons. Right now, when you go to O2, I'll have 16 electrons totally. One O will have 8 electrons, right? So now when you have 16, you cannot follow this. I have to follow some other thing. Let me tell you what I'm going to do. Everything else is same, right? If electron count is greater than 14 from 15 onwards, okay, all you have to do is just these two alone you interchange, right? So if I write it properly, it is going to be sigma 1s, sigma star 1s, sigma 2s, sigma star 2x, pi 2px equal to pi 2py. Oh, I'm sorry. I'm so sorry. This is not the thing which you have to interchange. Right? You have to interchange this and this. I'm so sorry. Right? So now this is wrong. Right? This would be sigma 2pz. Then comes pi 2px equal to pi 2py. Then comes pi star 2px equal to pi star 2py. Then comes your sigma star 2pz. So you see, the only difference is this between electron count greater than 14, electron count less than 14. And your homework is why. Why is there such a difference? You're going to tell me next class. Anybody wants to tell me now? Anyways, I don't think you'll know. But your homework is to find out why this is happening. Nobody's going to ask you in exams why this is happening, but it's a good thing to know. Just find it out. Google it. Okay? Find out the answer and tell me next class. I'll ask you. Why is there a difference like this? Okay. So in this order only, people, in this order only, you're going to fill the electrons depending on the electron count. Okay? Right. Now, again, each molecular orbital can have 2 electrons, right? Each molecular orbital can have 2 electrons. Okay. And what you have to make sure is not only off-course principle is satisfied, even your polys, right, and Hunts, both of them are also satisfied, right? That means till here, till when you come here, you can directly put 2, everything. But when you go to equal energy orbital, that is pi 2px equal to pi 2py, or when you go to pi star 2px equal to pi star 2py, first you have to put 1, 1, then you have to make it 2, 2. Hope you understand. Just how we do with p orbital. We do 1, 1, 1, then we put the pairing. Same way here also, first I'll put 1, another 1, then I'll go for pairing. Same goes with here also. I'll be very careful with this alone. Right? Other things are fine. You can directly put 2, 2, 2, 2 everywhere. Okay? This alone, be very careful.
Sir?
Right. Yeah, tell me.
Sir, what if there's only one electron? So, like, where will it go? Pi 2px or pi 2py?
Oh, it doesn't matter. It doesn't matter. You can put it in pi 2px or pi 2py. Both are equal energy. Doesn't matter.
Okay, sir.
Okay? Right. Fine. Okay. That is about off-course principle, polysubstitution principle, and your Hans rule of maximum multiplicity. Everything is fine. Everything is okay with us. Right? Now, next thing is we have to look into certain molecules. Okay, and how this works. Basically, I'm going to look into the bonding energy diagram, molecular orbital energy diagram. Okay, but we don't spend so much time on that because I don't know whether it will be even asked, because now since it's going to be only MCQs, I don't know whether it will be, but still we'll spend some time. It's very simple only. Okay, right. So now people, okay, we'll take an example as H2. H2 is a very simple example. We'll take it. Okay, H2 example we'll take. So now I know the molecular orbital configuration. No more we are going to speak about atomic orbitals, electronic configuration. We are going to speak electronic configuration in terms of molecular orbital. Only for a molecule, not for hydrogen atom. For hydrogen molecule only we can speak about molecular orbital electronic configuration. Right? Now it's very simple. It has only 2 electrons totally. Right? So the only possible is sigma 1s2. That's it. That's the configuration. Okay, right. Now we'll try to understand how I'm going to put the electrons. What is the energy level diagram and stuff. Okay, right. Now I have 2 hydrogens. Right. Now each is having 1s orbital. 1s orbital. This is having 1 electron. This is having 1 electron. No problem. Okay. Now I know 1s orbital can constructively interfere to form sigma 1s. Destructively interfere to form sigma star 1s, right? And I told you the bonding orbital should have lesser energy, anti-bonding should have higher energy, right? So it's very simple, guys. Now this and this will constructively interfere. This is the energy, okay? This is energy's y-axis. So obviously this is going to have lesser energy. Now this is the bonding molecular orbital. That is nothing going to be sigma 1s. Okay. Now again, they will combine again together destructively in this time to form sigma star 1s. Okay, now you have 2 electrons to fill, 1, 2, and since it is lower energy, both the electrons will go to sigma 1s, and there are no electrons in sigma star 1s. Even though it is there, it is an empty orbital. Okay, right? Fine. Now, another thing what you have to understand is, I told you molecular orbital theory predicts the stability, bond strengths, bond lengths, all of them can be predicted. Okay, for that there is a particular quantity which is going to help us, and that is what is called as my bond order. Okay, now bond order is nothing but the formula is very simple, guys. Basically, bond order tells me how many bonds are there. That's what bond order tells you basically, right? So I know between 2 hydrogen there is only 1 bond, right? Between O and O I have 2 bonds. Between N and N I have 3 bonds. Right? So like that, how many bonds are there? That particular number is given by bond order. Okay. Now it's very simple. The formula, it's half into number of electrons in bonding molecular orbital BMO minus number of electrons in an anti-bonding molecular orbital here. Right? Half into number of electrons in bonding molecular orbital minus number of electrons in anti-bonding molecular orbital. Now I can easily calculate for H2 here, half into, if you look at the configuration, only sigma 1 has 2 electrons and there is no electron in the anti-bonding. So 2 minus 0, there are no electrons in anti-bonding. So 2 by 2 will become 1. So I know that H, there is only one bond remain. Only one bond is there between hydrogen atoms. Very simple. Right. Now, what other things my bond order tells me is my BO bond order is directly proportional to the bond strength. Right. My bond order is directly proportional to the bond strength. Okay. And obviously, it is directly proportional to stability, because more and more is the strength of the bond, more and more is the stability of the molecule. Right. And I know how bond length and bond strength are related. If I have a strong bond, the atoms will be very close by. That means the bond length is less. Okay. So bond order is inversely proportional to the bond length. Okay. Bond order is inversely proportional to the bond length. Okay. These three things are very easily understood. Logical, very logical. Okay, fine. Now let us take another example. Like, let me take maybe O2, right? If this example we understand, we are done. Okay, for O2, let us write the electronic configuration first. Molecular orbital electronic configuration. Okay, so we write sigma 1s2, sigma star 1s2, sigma 2s2. So totally there are how many electrons? 16 electrons are there. Okay, one O has 88, two O's will have 16. Okay, right. So now I have sigma, okay, and then sigma star 2s2, and then now what should come? Sigma 2pz should come, because it is having more than 15, more than 14. So first comes sigma 2pz, then only pi should come, right? So now 2 electrons, and then pi 2px equal to pi 2py. Right. So now I have to put 1, 1, then 1, 1. But even if you do that, it is going to become 2, 2. So don't worry about it. Okay. So till now, how much got 1, 2, 3, 4, 5, 6, 7. Then I have to, now there are 2 more electrons left. So I have pi star 2px equal to pi star 2py. Now I cannot put 2 electrons directly here. I have to put 1 electron here, 1 electron here, because I have to follow Hund's rule of maximum multiplicity. I cannot put 2 electrons here. No, that's absolutely wrong. 1 electron here, 1 electron here. Okay. Now, yeah, tell me.
Sir, bond order can never be in fraction.
Bond order can be fraction. Why not? It can be 2.5. It can be 1.5. It can be fractions also. Right. What does that mean? Is that there is not a proper. If I say 1.5, right, that means there is one proper bond, and they say there is a partial bond 0.5. Right, I can have even bond order sometimes to be 1.33. Right, this will happen when I have resonance. We'll speak about this, but this is not there in the syllabus how it is 1.33 and all. But due to some phenomenon called as resonance, right, this can exist. Okay, yeah. So you're answering a question. Yes, bond order can be a fraction. Yes.
Sure. So can we say that in coordination, a bond, there's a bond order of fraction?
Sorry. Please go on. Come again.
In coordination bond, sir, there is a bond order of fraction. Can we say like that?
Correct. Whenever there's a coordinate bond, it is going to be 0.5. Okay. Sir. Whenever there is a coordinate bond, for that bond alone, we'll give a 0.5. Okay.
Okay,
right.
Sir.
Right. Okay. So this is the molecular orbital electronic configuration for O2. But what we'll try to do now is go for the molecular energy diagram, orbital energy diagram. Okay, I need some space, so let me go this side. Right. So first, oxygen. I have see. I don't have to do for see. There is 1s, 2s, 2p, and all. Fine, I will do for everything. But I should have some space. That's all I want. Okay. So oxygen this side, oxygen this side. Now say I have 1s, one space. 2s, another space, and 2pz, one space. This is 2py and this is 2px. Okay, right? Fine. Now again, same way for this oxygen, 1s, 2s, 2pz, 2py, and 2px. Okay, right. Now I know that, fine, we'll fill the electrons first. It is 1s2, 2s2. Okay, it's going to be 1s2, 2s2, 2p4, right? So 2p4 means 2p4 like this. Okay, same way, 2 electrons, 2 electrons, 2 electrons, 1 electron, 1 electron. Total atomic number 8. Okay, fine. Now let us draw the molecular orbital. Now 1s and 1s will constructively interfere to form sigma 1s and destructively interfere to form sigma star 1s. Okay, same way 2s and 2s will combine together to form sigma 2s and they will destructively interfere to form sigma star 2s. Okay, next coming to 2pz, 2pz and 2pz will combine together to form sigma 2pz and they will destructively interfere to form sigma star 2pz. Okay, now I need some space. Fine. Okay, let me adjust. Right. So now pi 2px and this 2px will form, I would say there are two orbitals going to form between px and py. This is going to be my pi 2px. This is my pi 2py. Same way, this and this and this and this will again form two orbitals, that is pi star 2px and pi star 2py. See, I don't have a space, but you can draw it legibly. Oh, I hope you understood how easily I'm drawing. Very simple it is. Right? Okay. Now I have to fill the electron. I have to fill 16 electrons. Right? Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's it. You can see pi star 2px and pi star 2py has one electron. That's exactly should come there. Okay, so any molecule given to you, it's very, very simple to draw the molecular energy, orbital energy diagram. It will take only 2 minutes for you to understand and draw it. Very simple, very, very simple. Okay, right. So that is about O2 molecule, right? Now I can calculate the bond order of O2. You should get 2, right? Because I know it is O double bond O, right? If you calculate, it is half into number of electrons in bonding. So 2, 4, 6, 8, 10. 10 electrons in bonding molecular orbitals, right? You can see all without the stars, right? And with the stars, you calculate 2, 4, 5, 6. 6 electrons, right? So 1 by 2 minus 4, 10 minus 6 is 4. So you'll find that the bond order is 2. Okay, very, very simple. Very, very simple. Right? Okay, fine. So that's about O2, right? Now I can see they can give any kind of molecule. Say they can give O2 plus, O2 minus, O2 2 plus. Now you know what you're going to do. So O2 plus will basically have 15 electrons, not 16 electrons. O2 minus would have had 17 electrons. O2 2 plus would have had 14 electrons. Right? It's very simple. From O2, remove 1 electron to form O2 plus. Right? So like this, they can ask questions also. And accordingly, you can find the bond order. Very simple. Okay, right. Same goes with N2. N2, if you check, same way you will find that it is going to have a bond order of 3. Right. But if you check for helium-2 people, if you check for He2 molecule, right? Now let us, I already have 4 electrons here. Okay, I have 4 electrons here. Okay, now how will I write the configuration? Sigma 1s2, sigma star 1s2, right? Now when I calculate the bond order, it is half into 2 minus 2, which will become 0, right? So when our bond order is equal to 0, that means the molecule doesn't exist. Right? But whenever you find the bond order is 0, okay, the molecule does not exist. Same thing will happen for Be2. You'll find that this molecule will not exist. Okay, right? So now you can predict whether theoretically the molecule will exist or not with the help of the bond order calculations. That's all. That's the whole point. Okay, any questions till now? Anybody has? Okay, I hope everything is clear. Right, now what you do is that time, so I don't know how many of you were there. We did a problem like Li2 plus, or say Li2 1 plus Li2 1 minus. Okay, right. Now, if you check, if I ask you to arrange them in the order of stability, right? If I ask you to arrange them in the order of stability, it's very simple. Whichever is going to have higher bond order, that is going to have higher stability. Okay, but if you do your calculations, this will have a bond order of 1. Okay, this 2, that is your Li2 1 plus and Li2 1 minus is going to have both of them will have a bond order of 0.5 and 0.5. Okay, right. Now in these kind of things, you have, whenever the bond order is not same, whichever is having higher bond order has higher stability. That is very simple, right? But if you find that the bond orders of two species are same, then what will you do? Is you have to look into the configuration, right? Now, the one with lesser number of electrons in ABMO is more stable. Or I can say it like this: the one with higher number of electrons in BMO is more stable. Right? So there are two ways of looking into it. If there are, now this will happen only if same bond order. Okay, only if there is same bond order. Okay, if there's a different bond order, obviously one with a higher bond order is having higher stability. Okay, right. Now in this case, you see that Li2 plus, Li2 1 plus and Li2 1 minus have the same order of 0.5 and 0.5. Right. So whenever you find this kind of situations, all you have to understand is for stability, there should be lesser electrons in anti-bonding orbital, because anti-bonding orbital doesn't favor bond formation. Right. And second thing is, if you find the number of electrons in anti-bonding molecular orbital is same, then what you do? Then you go for the thing which is having higher number of electrons in bonding molecular orbitals. Okay. Now, if you look at the example, you clearly understand. Say for Li2 plus, if I write the configuration, it will be sigma 1s2. Basically, Li2 plus would be 3 electrons. Okay, Li2 would have been 5 electrons. Okay, lithium has an atomic number of 3. Right. So Li2 will have 6 electrons. Li2 1 plus will have 5 electrons. Okay, fine. So sigma 1s, sigma star 1s2. One more electron would be sigma 2s1. This is for Li2 1 plus. Okay, next. Li2 1 minus, which will have 7 electrons now. Is it not? Li2 will have 6 electrons. Li2 minus would have had 7 electrons now, because 6 plus 1 will become 7. Now let me write. It would be sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s1. Okay, sigma star 2s1. Okay, right. Now I would say this doesn't give priority. The priority should be to this, right? Lesser number of electron to the bonding molecular orbital, anti-bonding molecular orbital. Now you see the number of electrons in anti-bonding molecular orbital in this case is only 2 electrons here, right? But you see here the number of electrons in anti-bonding molecular orbital in this case is 2 plus 1, 3, right? So I can blindly say that Li2 1 plus is more stable than Li2 1 minus, because Li2 1 minus has more number of electrons in anti-bonding molecular orbital, that makes it unstable. And obviously Li2 is the most stable because it is higher bond order. Very simple. Okay, I hope this all made good sense to you. Very good sense. Right? Any question whatsoever? Is it there? Okay, that's it. That is about molecular orbital theory. Okay. Oh yeah, wait, I didn't forget. I almost forgot. Magnetic properties. Okay, magnetic properties. First of all, you have to understand what do you mean by magnetic properties. Magnetic properties are nothing. I have a molecule with me. Okay, I bring a magnet near that particular molecule. How that molecule reacts to that particular phenomena. When I bring a magnet, how that molecule interacts with the magnet is the question. Right now, when I bring a magnet, right? When I bring a magnet, when I say magnetic properties, it can be of three types. Is it not? One is getting attracted towards the magnet, right? That is one possibility. The molecule gets attracted by the magnet, right? For example, iron molecule, right? You know, any ion will get attracted towards the magnet, and say it can repel the magnet. It can repel the magnet, right? Or there will be no effect, neither attraction nor repulsion, right? Neither attraction nor repulsion. Okay, so three possibilities: either the molecule can get attracted towards the magnet, or get repelled by the magnet, or say there is no effect in bringing the magnet. Whether the magnet is there or not there, the molecule is not going to vary much. Okay, right, fine. Now, this attraction can again be of two types. Attraction and repulsion can be of two types, in the sense that this can be a permanent effect, right? Say permanently it is getting attracted, right? Now, or instead of talking like this, we'll talk like this. Okay, right. Now, for us to understand this, okay, now all you have to understand is the arrangement of atoms, the arrangement of electrons, right? The arrangement, this is an atom. Okay, the arrangement of electrons inside the atom will be randomly oriented. Okay, then there is no magnet. Okay, now what happens when I bring a magnet? This is a magnet, right? What happens when I bring a magnet? Right, now the first possibility is, I say this is the direction of the magnetic field. Okay, this is the direction of the magnetic field. Okay, now there is first possibility is, now this is the direction of magnetic field. The electrons can arrange themselves in the direction of magnetic field, right? Whatever is the direction of magnetic field, the electrons can also align themselves in the direction of magnetic field. Now this is my attraction. Okay, now the other possibility is, when I bring a magnet and say this is the direction of magnetic field, right? Now the electrons can align themselves in the opposite direction of the magnetic field. Now this is my repulsion. Okay, this is my repulsion, right? The same direction, aligning themselves, attraction. If they align themselves in different direction, it is going to be repulsion. Okay, and if nothing happens, if the presence of the magnetic field, if it still stays like this only, randomly oriented, now that is no effect, right? That we cannot talk. There is no, that particular compound has no magnetic properties. That is how we tell it. Okay, obviously this is not our concern, right? But we are going to consider on these two. Okay, now this attraction, as I told you, can be temporary or permanent. What do you mean by temporary and permanent? Means, so for example, permanent means even after my removal of magnetic field, even if I remove the magnetic field, the alignment is same. That is, they are not going to go back to this state. Once magnetized, right? This phenomena is what is called as magnetization. Okay, now once the molecule is magnetized, even if I remove the magnetic field, they are going to stay as such. That is what is being permanent, right? But once I remove the magnetic field, and if they go to their original random position, that is my temporary effect. Okay, that is my temporary effect. Same goes with the repulsion also. Once I remove, like say if it is permanent, even after the removal, see there's no magnetic field, but still the alignment is same. This is permanent effect. Or it can be a temporary effect, where after remove the magnetic field, again they go back to their original random positions. Okay, people. Right. Now, we have to give some names to this. Okay. So the molecules which are getting attracted and they have a permanent effect, permanent magnetic effect, these kind of substances are what are called as ferromagnetic substances. Okay, when they have a permanent effect, first they have to align themselves in the direction of magnetic field, obviously attraction. But once they remove the magnetic field, if it still stays as such, these are what are called as ferromagnetic substances. Okay, right. Now, when they get attracted, but if it is going to be a temporary effect, right? Those kind of molecules are what are called as diamagnetic. Am I correct? Is it diamagnetic or paramagnetic, people? Any idea? Okay, fine. It is diamagnetic only. Okay, these are called as temporary attraction. Is what is called as. Excuse me. Right, it is called as that. These kind of molecules are what
Sir,
are called.
can you repeat once again?
Sure, sure. Right. So first, did you understand attraction and repulsion, Kanna?
Yes, sir. The diamagnetic, can you like repeat it once again?
Yeah, sure. So what I'm telling is, when I have a permanent effect, in the sense that even after I remove the magnetic field, if they're going to stay like this only in the direction of how the direction was the magnetic field was, right, then they are called ferromagnetic, right? But when I remove the magnetic field and if they go back to the previous position, how they were, those kind of things are called as diamagnetic. Basically, diamagnetic substances will get attracted towards the magnet only till the magnet is there. Or I would say they are magnetized only when the presence of magnetic field is there. If there is no magnet, once they remove the magnetic field, now again they go back to their original position. That is random orientation. Yes, understood?
Yes, sir. Got it.
Right, good. Right, same way people here, right, when they get repelled permanently, right, these are what are called as anti-ferromagnetic substances. Okay, anti-ferromagnetic substances. Okay, right. Now, when I have a temporary effect of this, these are what are called as paramagnetic substances. Okay, these are what are called as paramagnetic substances. Okay, so permanent effect, permanent repulsion is antiferromagnetic, temporary repulsion is paramagnetic. Same way, permanent attraction is ferromagnetic, temporary attraction is diamagnetic. Okay, I hope this all is very clear. Okay, right. Now, I just have one more thing to you. The one more thing is there's no effect, right? This no effect can be of two types. Okay, right. One is literally no effect. The bringing in a magnetic field does not change anything. Whatever is the orientation, that orientation stays. The other way I can think about it is that, say, look at this. This is the magnetic field. Okay, when the magnetic field is not there, say random orientation. Okay, now when I apply the magnetic field, say assume that there are 4 electrons here. Okay, now the 2 electrons will align themselves in the direction of magnetic field. 2 electrons will align themselves in the opposite direction of the magnetic field. So net effect is 0. Right? 2 electrons getting attracted, 2 electrons repelling. So eventually there is no effect. Right? So this no effect thing, this overall no effect can be of two types. One is literally no effect, that there's nothing changing. Whether there is magnetic field or no magnetic field, this is going to stay as such. That is one way. Other way is when there is no magnetic field, obviously random orientation. But when there is magnetic field, to say if at all 4 electrons are there, 2 of them will align themselves along the direction and 2 of them will align themselves in the opposite direction. Right? Now, these kind of substances are what are called as ferrimagnetic substances.
Sir?
Okay? Yeah, tell me.
Sir, can we say that ferromagnetic is also no effect thing?
Ferromagnetic, how is it no effect?
Sir, even if there is magnetic field, they align themselves in a particular direction. And even if there's no magnetic field, they still remain the same, right?
Correct. But first of all, for you to must make them align in the direction, you have to first bring in the magnetic field. If magnetic field is not there, this is the random orientation only will be present.
So after the magnetic field is removed,
exactly.
It will stay.
Exactly.
Okay, sir, got it.
Right. Good. Right. So I hope everybody understood. There are 5 types of magnetic substances. Paramagnetic, diamagnetic, both are temporary effects. Ferromagnetic, antiferromagnetic, both are permanent effects. Ferrimagnetic substances are like they say that there's no effect, we can say, but still the inside something is happening. Okay, 5 types of substances you can have. Okay, now why did I teach you this is because with the help of molecular orbital theory, right, you will be able to predict whether the molecule is paramagnetic or diamagnetic. Then don't ask me, sir, can I not predict ferromagnetic and antiferromagnetic? No, you cannot predict. Okay, only when you do the experiment, right? Only when you do the experiment, we'll be able to tell whether it is going to be ferromagnetic, or that is whether it's permanent effect or not. I can tell only when they do the experiment. But temporary effect, yes, with the help of the electronic configuration itself, I'll be able to predict it. Okay, right. So diamagnetic and paramagnetic, we'll see how to predict them just by looking at the molecular orbital configuration. Okay, it's very, very simple, people. The simple thumb rule is if there are unpaired electrons in the molecule or in the MO electronic configuration, right, that becomes a paramagnetic substance. Right, that becomes a paramagnetic. So O2 is paramagnetic, is it not? Because I had pi star 2py1 equal to pi star 2px1. You can see there are unpaired electrons here. Unpaired means they should be like this. Paired means it should look like this. When all the electrons are paired, then it is going to become diamagnetic, right? Even if one of them is unpaired, right, and that is going to become that is going to make the molecule to be paramagnetic. Very, very simple. Just blindly you can say. Okay, so yeah, with this, your what is that? Molecular orbital theory is done. Okay, any questions anybody has? What is the time? Okay, any questions, people? Okay, now the last part of the chapter is going to talk about the secondary bonds. When we started this chapter, I told you that chemical bonds can be of two types. One are what are called as primary bonds. The other one are what are called as secondary bonds. Right? What is the basic difference, people? Can anybody remember? Remember and tell me what is the basic difference between primary and secondary bonds? What is the basic difference? So covalent bond, ionic bond, all these things came under primary bonds. Now secondary bonds are going to be a little different. What is the basic difference here between primary and secondary bonds?
In primary bonds, there will be a transfer of sharing of electrons.
Okay.
And in secondary bonds, there will be attraction between the charges.
Okay, it's a very crude answer because say even in an ionic bond, right, I have attractive force between positive and negative, right? Cation and anion. How I told you a perfect way of defining it. What is that way? How do you exactly define primary and secondary? What is the basic difference? The clue is
the primary
theory.
bond is it's strong bond because there's involvement of charges and all. Whereas secondary bond is comparatively less stronger than the primary bond.
That is for sure. Primary bonds are obviously stronger. Secondary bonds are weak. I want to know why is it happening. That's what I'm telling you. The clue is Dalton's theory. One of the points in Dalton's theory explains this. Not explains this, at least that's the clue for this.
So primary bonds have electronic repulsions and attractions between them.
No, not exactly. Oops, I'm sorry. What happened?
No sharing of electrons takes place in the secondary bond.
See, you are telling everything fine. There is transfer of electron, sharing of electron in primary bond, and there is no such thing in secondary bonds. But how exactly do you put it? Like I'll give you 10 more seconds to think about it. I'm going to give the answer or else. I gave you the clue. The clue is Dalton's theory. One of the postulates of Dalton is the one which is going to help me here. Okay, I think the time's up. So remember people, in primary bonds, there is permanent change in the electronic configuration of the atom. Right? That means electron is completely lost, completely gained, or say completely shared. There is permanent change in the electronic configuration. Okay, or this is how we call it, complete rearrangement in the electronic configuration. Right? So what Dalton said? Dalton said that atoms undergo some kind of rearrangement during a chemical reaction or say a bond formation. Where is rearrangement happening? Obviously, it is happening in the electronic configuration of an atom. Right? Now, if this rearrangement or say if this change in electronic configuration is permanent, perfect, like that is going to be your primary bond. Right here, it is going to be, it does not say complete rearrangement is the correct word, right? We cannot say permanent rearrangement. Okay, right? We can tell that here in case of secondary bonds, it is going to be a partial rearrangement in the electronic configuration. Right? The electron is not completely lost or completely gained, or neither it is not completely shared. It is somewhere hanging in between in case of secondary bonds, and that is why obviously secondary bonds are weaker than primary bonds. Okay, and one more basic difference is primary bonds bind atoms. Obviously, two hydrogen atoms together will make a covalent bond. Na plus and Cl minus will form an ionic bond. All these are atoms, right? So primary bonds are for the attractive force between atoms, right? Secondary bonds are attractive forces between molecules. Right. Now, please understand, people, I have a tumbler of water. Okay. I have a tumbler of water. If I take one water molecule and check, obviously I have two OH bonds. Very simple. Right. But, I know in a tumbler of water, I can have millions and billions of water molecules. Right. I can have millions and billions of water molecules. Right. So now, how are these water molecules able to stay together? Right? There should be one water molecule is here, another water molecule is here. Only if they have some kind of force existing, attractive force existing between them, they'll be able to stay together, or else they'll just walk away. Right? You will find only, like, if at all this force is not there, right? If this attractive force between two water molecules, I am not telling between hydrogen and oxygen. No, I am telling between two water molecules. Right? If this force was not there, obviously you will see only individual molecules everywhere. And that is not the case, isn't it? Everywhere you see collection of millions and billions of atoms, or I should not say atoms, molecules are together. Say HF molecule, HCl molecule. It's not that only one HCl will be there in an acid, is it not? There'll be thousands and millions of HCls. How are they together? Why are they not moving away? Everything is, they are stabilized, right? Hydrogen is stabilized, oxygen is stabilized, right? They can stay together. I mean, they can stay away from each other. Why are they staying each other? Because that is going to bring in more stability, right? If they are together, that is going to bring in more stability. That's the answer to the question, right? Now we'll try. Now we understood, right? What do you mean by secondary bonds? Secondary bonds are the bonds which binds molecules together, not atoms. Right? Two molecules, H2O molecule, H2O molecule, HF molecule, HF molecule, HCl molecule, HCl molecule. Right? Or say even oxygen for example. Is it there? Is it like you have oxygen in the air, right? Is it like when you breathe, right? Only one oxygen atom goes inside. Sorry, only one oxygen molecule goes inside. No, there'll be thousands and millions of O2s which will go inside you because they are together. If they are very far away from each other, obviously when you breathe in, right, individual O2 molecules will go inside, and that is never going to happen in reality. Why? Because these secondary bonds exist which will bind two O2 molecules together, or say 1000 O2 molecules together. Right? Okay, so that is what we're going to study now. How are these bonds, how are these molecules held with each other? How are they connected? Okay, right. Now, obviously, it cannot be one answer. right? It cannot be just one type of secondary bond which will answer everything, right? There should be different, how we have covalent bond, coordinate bond, ionic bond, depending on the conditions. Here also, depending on the conditions, I can have different types of secondary bonds, right? Now, what are the things we'll first list it out. First one, I'll call it as dipole interaction, right? I can write actually dipole interaction, okay? Or it can be a dipole ion interaction, okay? Or it can be hydrogen bonding, very important. Hydrogen bonding we'll see in depth, right? Or I have something called as van der Waals force. Okay, we'll study all of them in depth now. What is the time? Okay, we have half an hour. I'll be able to complete it. Okay, fine. So these are all the different types of secondary bonds I can have in chemistry. Okay, now let us start with dipole interactions. It's very simple to understand. Okay, now from the name itself you can understand one dipole and another dipole are there together somehow, right? Now the example I can take is, say, HF molecule. Okay, now HF molecule, say another HF molecule I have, right? Now I know this bond is polar. Now remember that this will happen for polar molecules only. Okay, this will happen for polar molecules only, because dipole will exist only for a polar molecule, only if there is electronegativity difference. Right, now I already know that there is going to be, because of the electronegativity difference, fluorine is going to have a partial negative charge and hydrogen is going to have a partial positive charge. This is a dipole, right? What is a dipole? Equal and opposite charges separated by a distance, right? Equal and opposite charges separated by a distance here. This is a dipole. Now, same thing will happen with this also. There'll be a del positive and there'll be a del negative, right? Now you see, this is one dipole. This is another dipole. I am going to have attractive force between this del negative and this del positive. This is the attractive force. Same way, I can just continue doing this, right? I can have one more HF molecule. Again, del positive, del negative, again, an interaction between these two, right? This is what is called as your dipole interaction. Okay, two dipoles are there, partial charge negative, partial charge positive. The next one, partial charge positive, partial negative. The partial positive of one molecule will have an attractive force with the partial negative of the next molecule. Okay, this is what is called as your dipole interaction, which will be existing only in polar molecules. Again and again, I'm repeating. This will not be there in H2. This will not be there in Cl2. No, they have different kinds of force. We'll see that. What is that? Okay, now they will directly go to hydrogen bonding. Okay, now hydrogen bonding is a special type of dipole interaction. Okay, hydrogen bonding is a special type of dipole interaction. Right, now, fine. Now for hydrogen bonding to happen, okay, I would say this, whatever we wrote here is an example for hydrogen bonding only, but we'll speak in detail. Okay, you understood what is the dipole interaction, that we understood, right? Now, for hydrogen bonding to happen, people, there are two requirements. Okay, now the requirement is I should have something called as hydrogen donors and I should have something called as hydrogen acceptors. Okay, I should have something called as hydrogen donors and I should have something called as hydrogen acceptors. Right, okay. Now, what do you mean by hydrogen donors? What do you mean by hydrogen acceptors? Is very simple. Hydrogen donors means hydrogen should be attached with the highly electronegative element. Right? There should be one hydrogen and this hydrogen should be bonded to a highly electronegative element, and there are only three possibilities. Right? The electronegative element can be oxygen, nitrogen, or fluorine. Only three. Right? So if you find the OH bond or an NH bond or a FH bond, only those three types of bonds are capable of involving in hydrogen bonding. That is about hydrogen donor. Yeah.
Sir, why not chlorine?
Yes, chlorine is not that electronegative. So the thing is, there should be some del positive, right, on hydrogen. Obviously, these are more electronegative, they'll have del negative. Hydrogen should have a del positive. Now, for this kind of dipole-dipole interaction to be considered hydrogen bonding, right, there should be some minimum value of del plus. Okay, say for example 5, right? There should be a minimum value of 5 for it to be considered to be hydrogen bonding. If it is less than 5, it will go under the category of dipole-dipole interaction again. Right? So chlorine is not able to produce that much del plus to be called hydrogen bonding. So it goes into the category of dipole-dipole interaction. Okay? Okay, sir. They get the point? Okay, good. Right. So that's about hydrogen donors. Okay, only 3 elements are capable of forming hydrogen donors. That is when hydrogen is attached to oxygen or nitrogen or fluorine. Okay, now what are hydrogen acceptors? Hydrogen acceptor is very simple. Anything with a lone pair. Right? Anything with a lone pair can be a hydrogen acceptor. Okay, anything with a lone pair can be a hydrogen acceptor. Right? Now, it's not that only hydrogen donor should be present. It's not that only hydrogen acceptor will be present. Both of them should be present. Okay, both of them should be present. Now, sometimes what can happen is one molecule itself, right? One molecule itself can act as hydrogen donor as well as hydrogen acceptor. Right? And sometimes what will you see is one molecule will act as hydrogen donor, an entirely different molecule can act as hydrogen acceptor. Okay, right. So we'll take both the cases and see what exactly is this. Right. Or first we try to understand what is hydrogen bonding. How it is the hydrogen donors, what is hydrogen acceptors, how they are going to form the hydrogen bonds, all we'll try to understand. Okay. Now the best example I can take is the example of water. Is it not? Because you see, I have a OH bond, basically hydrogen donor tick, right? And I know oxygen has lone pair on it, so hydrogen acceptor tick, right? So these kind of molecules can act as both hydrogen donors as well as hydrogen acceptors. But say, let me take a molecule like this. This is acetone. Right? Now, can this act as hydrogen donor? Can this act as hydrogen donor?
No, sir.
Why? Because obviously there is no OH bond or NH bond or FH bond. None of them are there. Only CH bond is there. That is impossible. That cannot be involved in hydrogen bonding. Right? But can it be a hydrogen acceptor? Can it be a hydrogen acceptor?
Yes, sir, I think.
Yes, easy, right? I have two lone pairs on oxygen. So this can act as only hydrogen acceptor. Right? So for this to involve in hydrogen bonding, there should be some other molecule which should act as a hydrogen donor. This alone cannot involve in hydrogen bonding. Right? Say acetone, when it dissolves in water, then I can have hydrogen bonding. Right? But only this is there, acetone solution is there, that cannot have hydrogen bonding. Okay, because the hydrogen donor capabilities are not there. But look at water molecule, or say look at HF molecule or an ammonia molecule. I have a NH bond, so hydrogen donor. Okay, now I have a lone pair on nitrogen, so hydrogen acceptor. Okay, same with HF. Right? Hydrogen donor, okay, because I have a HF bond and it has a lone pair. So both the things are okay. I don't need anything extra for me to have hydrogen bonding. Between two HFs, between two H2Os, between two ammonia molecules, I can have hydrogen bonding. But between two acetone molecules, I cannot have hydrogen bonding. Right? Both the things should be there for me to have hydrogen bonding. I can have hydrogen bonding between acetone and water. That is okay. Right? But only acetone, no, I cannot have. Right? But HF, H2O, NH3, all of them are capable of forming hydrogen bonds with themselves, because both the capabilities are there. Both hydrogen donor capabilities as well as hydrogen acceptor capabilities are there in all these three molecules. There are so many molecules, even alcohol, CH3OH. Now see, I have a OH bond and oxygen as a lone pair. Any alcohol for that matter will again have hydrogen bonding. because both hydrogen donor as well as hydrogen acceptor is there. Okay, right. So for next, so we understood what kind of molecules can form hydrogen bond with themselves and what kind of molecules cannot. Right. Okay. Now we'll try to understand how exactly is this. Right. So let me take H2O molecule. Okay. Now I know I'm going to have a del negative, del positive, and del positive. Okay. Let me take another water molecule. Right. Now in this case, I take okay, there are two ways of looking into it. I'll tell both the ways. Okay, now I can see that it is a dipole-dipole interaction because this del positive can interact with this del negative. Hydrogen bond, this is exactly what is called as hydrogen bonding. Now this is one way of looking into it. The other way of looking into it is this del positive can get attracted by the lone pair of electrons which is present on the oxygen. Anyway, this is also positive. This is negative charge. Again, lone pair is a negative charge, right? So either you say that there is a interaction between del positive and del negative, or you understand in a way that there's going to be interaction between del positive and the lone pair. Both are right. Okay, but I would say the interaction between del positive and lone pair will be more used, right? It's not that that should be only used, but it is more easier for us to understand certain phenomena if you understand this. Okay, so all you have to understand is that the del positive and the lone pair on the oxygen on the next water molecule will have an attractive force, and that is what is called as your hydrogen bonding. Right? Same can happen between this lone pair and this hydrogen. Right? Another water molecule is there. Again, I can have that also. Right? So this is what is called as hydrogen bonding. Okay, same goes with your HF. I'll take ammonia as an example and I will try to understand. Right? Lone pair. Say, right? Say there is lone pair here, right? Now there's a del positive, del positive, del positive. Now say I can have an interaction between the del positive and the lone pair on nitrogen. Same way, this hydrogen and the lone pair on this nitrogen can have an interaction like this. Okay, this is what is called as hydrogen bonding. Right. Now, people, hydrogen bonding can be of two types. Right. One is what is called as intramolecular hydrogen bonding. The other one is what is called as intermolecular hydrogen bonding. Okay, intramolecular hydrogen bonding and intermolecular hydrogen bonding. Okay, now it's very easy to understand this. Inter-school competitions and intra-school competition. Intra-school competition means within your same school you compete. Say sports day is an example for intra-school event. Annual day is an intra-school event, right? But when you go to culturals of another school, say you go to a sports competition to say some other school, that becomes an inter-school competition between two different schools, right? If it is going to happen in the same school, intra-school competition. If it is going to happen between two different schools, it is going to be called as inter-school competitions. Same analogy goes with here also, right? Now here, there is only one molecule required. There are no two molecules, right? They're not like two H2Os, one H2O, no. Like one molecule will only be there. That is capable of doing hydrogen bonding, right? And obviously here, I require two molecules. Of the same thing or different thing, doesn't matter. H2O, or say H2O acetone, doesn't matter, but I require two molecules, right? But here, one single molecule, in the single molecule itself, I can have hydrogen bonding. Now, till now, what we saw are intermolecular. We saw H2O, NH3, HF, all these things can have intermolecular hydrogen bonding. Right. Now, if at all I have to give you an example for intramolecular, like say, you can remember this. Okay. Now, this is benzene ring, right? Hope you all know benzene ring. Everybody knows benzene ring? Can anybody give me a no? If they don't know, please. Okay, it's completely all right. Do you know benzene ring? C6H6. Do you know?
Yes, sir.
Okay. Is there anyone who don't know? You can see, be frank and tell me. Nobody is going to judge you. Especially I'm not going to judge you. Don't worry about your friends. right? What about anybody is there who doesn't know C6H6 structure benzene? This is how the structure looks. Okay, all these are carbon atoms, right? Now I have an OH here, right? And say I have CO CH3 here, C double bond. Okay, right properly. Okay, right. Now you see this bond, if I write it properly, one second. Okay, now this hydrogen will have a del positive. Okay, right. Now this oxygen will have a lone pair. Now I don't need another molecule. I can have interaction within the same molecule itself. I do not need another one. Right. Now this is what is called as intramolecular hydrogen. Okay, hydrogen donor and hydrogen acceptor capabilities are there in the same molecule. See, it's not like, I mean, two different points. One point has hydrogen donor, the other point has hydrogen acceptor. They can have interaction in the same molecule itself. I do not need one more molecule of this to have hydrogen bonding. No, not required. This one molecule itself is sufficient. Okay, this is what is called as intramolecular hydrogen bonding. Right, but all you have to remember is intermolecular hydrogen bonding is stronger. Okay, intermolecular hydrogen bonding is stronger than intramolecular hydrogen bonding. Okay, that means between two molecules, if I have hydrogen bonding, right, that is stronger than when I have in the same molecule. Okay, right, fine. That is about, okay, now let us take an example where like I have one molecule to act as, one different molecule altogether will act as a hydrogen donor, one molecule altogether will act as a hydrogen acceptor, right? Say the example can be acetone, which you took, right? Now acetone alone, no hydrogen bonding, but when I dissolve acetone in water, then I can have hydrogen bonding. How? Very simple. I have HOH, right? Now this can be del positive. I have a lone pair. I can have hydrogen bonding between water molecules. Water molecule in this case is going to act as hydrogen donor, and this is going to act as hydrogen acceptor. Right? Now this is also intermolecular only, right? But intermolecular hydrogen bonding between two different molecules altogether. Okay, right? This can also happen, right? Now we understood. Is there anybody who has any kind of question regarding hydrogen bonding? Anybody has any question, any clarity, anywhere required? Okay, I understand. I hope that everybody understood. Right now, what are the consequences?
Sir?
Yeah, tell me.
Sir, the distance between the intramolecular hydrogen bonding is more than that of intramolecular
Yes,
hydrogen
I
bonding,
understand
right?
what you're telling. Obviously, the distance here, right, they should be close enough to form hydrogen bonding, right? But if I have a molecule like this, I have a OH, right, and say I have a COCH3 here, right? Now the distance is very large that this cannot have intramolecular hydrogen bonding, but this can have intermolecular. How? No. Right, say COCH3, whatever. Now you see that del positive and the lone pair can have hydrogen bonding. This is intermolecular. Okay, but for intramolecular to happen, these two should be very close to each other. Only if they are to the next atoms, then it is possible. If not, these kind of things are there, but this is not going to happen because there are two bulky rings like this, which will not make sure that these OH and this OH are coming close by. But yeah, theoretically we can say that this can happen, right? But intramolecular is not possible in this case. That's what you have to understand, because they are very far away from each other.
Okay, sir.
Right, fine. So now, what are the consequences? Right, if hydrogen bonding happens, right? If there is a molecule, say for example, water, right? See, I'll give you a very classic example. Okay, H2O and H2S. Okay, actually no, forget about it. right? Now, okay, fine. What are the consequences? Right now, why I didn't take it, because I have to explain your van der Waals force and all, right? Or actually, I can do this. I will take H2O or leave, no problem. So, what are the consequences? Right? If I have hydrogen bonding, for example, water can act as hydrogen donor as well as hydrogen acceptor. Right now, you see, let me give you this point now. Right, for boiling point or melting point, generally we say that higher the molecular mass, higher will be the boiling point or melting point. We'll see why next class. Okay, right? Higher the molecular mass, or higher, I would say, the total number of electrons present, more will be the boiling point or melting point for that particular species. Okay, right. But when I compare H2O and H2S, what do I expect? I expect H2S to be having more boiling point. Right, H2S to be having a more boiling point, right? Or in other words, if you check at 25 degrees Celsius at room temperature, H2O is a liquid, right? But H2S is a gas, right? H2O is a liquid, whereas H2S is a gas, right? Now, even though H2S has more molecular mass, you can see more molecular mass means more boiling point. Right, but what we have in reality is that H2O is having more boiling point. It's understood from this itself. At 25 degrees Celsius, H2O is a liquid, but H2S is a gas. That means obviously this can easily go into the vapor phase, but H2O cannot go into the vapor phase that easily. Compared to this, obviously, I have to go to 100 degrees Celsius for this to happen. Right, now why is because H2O I can have hydrogen bonding, right, but H2S there is no hydrogen bonding. Right, now please understand, people, right, for anything to be a liquid, when I compare a liquid and a gas, what is the basic difference? Right, we have to go back to your 9th class, right? 9th or 10th class, 9th class, right? So solids, liquids, gases, right? So there is something called as intermolecular forces. Right, now intermolecular forces are nothing but the secondary bonds, people, between two H2O molecules, between two HF molecules, between two ammonia molecules. What force exists? That is what is called as your intermolecular forces, and those are nothing but secondary bonds. Right, now obviously for a solid, the intermolecular forces are very strong. They're very strong, that the molecules are very, very, very close by, and they're going to form a very good structure, like a very strong structure. Right, now obviously in your liquid it is little intermediate, right, and for gas it's the minimum value. Right, now intermolecular forces are not so much. That's why the molecules are very far away from each other. That's why it's a gas molecule. Right, okay, so what I understand in this case is that when you compare the distance between two H2O molecules, they are very close to each other. But when I compare the distance between two H2S molecules, they are very far away from each other. That's why it's a liquid. That's why this is a gas. Right, now what makes two H2Os to come together very closely is nothing but the hydrogen bond. Right, but here you will see I have only dipole-dipole interaction. Okay, so what you have to understand is hydrogen bonding is always stronger than dipole-dipole interactions. Okay, that's the reason why two H2O molecules are very close, forming a liquid, right? But H2S, even though it has more molecular mass than H2O, right, it is still a gas which is having lesser boiling point. Okay, this is one consequence. The first consequence is hydrogen bonding is there, right? Generally, it is directly proportional to the boiling point or melting point. Okay, more hydrogen bonding means more boiling point or melting point, right? Another thing is, mostly when I have hydrogen bonding, even low molecular mass compounds are or can be in liquid states. Generally, low molecular mass compounds will be in gaseous phase. Okay, they can be in liquid phase or solid phase for that matter, sometimes. Yes. Okay, right, that is the first consequence. Second consequence is solubility. right? Second consequence is solubility. What is the time? Okay, let me take 2 more minutes. I'll complete this. Okay, now what happens? See, generally, right? Generally, you have to remember this. I think we already spoke about this. Like dissolves like, right? We already know this. We have one type of substance, we have 2 types of substance. Polar substances or polar solutes will get dissolved in polar solvents, right? And non-polar solutes will dissolve in non-polar solvents. We already know this, right? But you see, a compound like acetone, right? A compound like acetone, right, is actually little non-polar. Even though I have a CO bond, it is not that polar. Okay, it's polar, right? So I expect that this is, yes, any doubts? Okay, so I expect that this is not going to be that much soluble in water. Is it not? It is not going to be that much soluble in water. Okay, but due to hydrogen bonding, I think I've already mentioned this, right? Due to hydrogen bonding, right, which is possible here, they can undergo very good solution. They can form a very acetone is highly dissolved in water, not because it is polar, but because it can form hydrogen bond. There are so many molecules like this. Okay, so any molecule which is little non-polar but still can form hydrogen bond with water will be highly soluble. Let me write it here. Even though non-polar, right? But if it can form hydrogen bonding with water, right, the compound is highly soluble in water. That's the second consequence. Okay, first consequence is, even though I have low molecular mass, if I have hydrogen bonding, I can have higher boiling point or melting point, and can be in gaseous or this is not gas, right? Liquid or solid state, right? Or if at all, even though the molecule is non-polar, I expect it to be not soluble in water. But if it can form hydrogen bonding with water, then the compound will be highly soluble. The best example I can have is acetone here. Okay, all these things are okay, right? We'll continue. We'll talk further about this hydrogen bonding next class. Any questions anybody has? There's something in the chat. What happened? Oh, okay. Right. So I think I can stop right here, no? Right. And I think everybody is fine with their doubts. Is there any questions anybody want to ask me?
Clear.
Okay. Okay. Fine, people. Thank you so much. We'll meet again next week.
Thank you, sir.
Thank you. Thank you.